Welcome back. The next topic we'll talk about is something called clocked circuits. In order to motivate this, we need to talk about something called asynchronous logic. So here is the Andor latch that we saw before. In its current state, the latch is on. When you flip the off switch, this thing should turn off. But one key point to mention is that each step in this process takes time. And this is sort of what we discussed in the last video. When I turn this off switch on, this wire turns on, which feeds a 0 through the NOT gate. Then there are 2 zeros going into the AND gate, which then change the previous on state to an off state. And then you get an off going into here, which sends an off through here, and the system is stable. But the point is that there were steps, right? First it went through this NOT gate, then it went through the AND gate, and then it went to this light bulb and to the OR gate. And each of these steps takes time. Now, if I had turned the ON gate on immediately after I turned, if I had turned the ON switch on immediately after I turned the OFF switch on, and had not waited for this signal to propagate through here, we may have potentially had something unexpected happen. Right, a 1 may have gone through here, which may have changed the behavior of this circuit. So really, if I want this to work, when I flip a switch and change the input, the circuit needs enough time to stabilize before I then change the inputs again. In this particular case, the circuit is stable, meaning whichever inputs I give it, it will give me some stable state of the system. But that takes time, and if I try to mess with the inputs before that stabilization has taken place, then I may end up with problems. In this particular case, you might think that this system is simple enough that the problems won't really matter, and you may be right. However, if you think about a computer, there are millions of these things being laid out on a board, and if you suddenly have all these errors where wires are firing at the wrong times, then everything might start breaking. This is a problem, and this is a problem that one needs to account for. One way to do this is using a clock. The reason it's called a clock is because, well, we use a clock, and it's a similar sort of idea. On our clock, there's 60 seconds in a minute, 60 minutes in an hour, 12 hours in a full clock cycle, or 24 hours in a day, if your clock can keep track of that. So there are a lot of different states of time that your clock can be in. And we use these different states to measure how long it takes to do things, or when we're going to meet people, or general scheduling tasks. A computer has the same sort of notion, except that a computer only has 2 states in its clock, on and off. This is a familiar theme. So this clock is some element of your circuit which turns on, and then it turns off, and it turns on, and then it turns off, ad infinitum. And the point is that the clock changes at a regular interval. So, for instance, this might happen every half a second or every half a nanosecond, depending on how fast the processor is. And the point is that the clock speed is much, much, much slower than the speed of electricity. Which means in particular that when I change the clock, I'm giving the circuits in the logic gates enough time to stabilize before I turn the clock to the next state. So if I turn the clock on, a bunch of different things happen in my circuit because they're allowed to receive input. That takes some time, but eventually that stabilizes. And once it stabilizes, I can wait and then turn my clock off. The point is that the clock speed is slower than the speed it takes the time it takes for the circuit to stabilize. Schematically, you can look at what's going on in this circle. So the clock turns on, data flows through the circuit stabilizes. Once it's stable, you know that it's safe to turn the clock off, but you give yourself a lot of extra time to make sure that this actually happens quickly enough. So you pause, and then you turn the clock off. Once the clock turns off, you're allowed to give new inputs into your system, and data flows through the circuit with these new inputs. The circuit stabilizes again. Then you pause to wait and give yourself enough time for the circuit to actually finish stabilizing. Then you turn the clock back on. And the point is that the amount of times that it takes for these first 3 steps is relatively small, but then the pause is much, much, much bigger. That ensures that the system is synchronized and is not an asynchronous logical system. Let's look at an example. We're going to do a different version of the Andor latch that I introduced before, where I put this Andor latch on the clock. On the right-hand side, you can see the familiar AND/OR latch. Here's the OR, here's the AND, and here's the NOT gate. They're organized in the exact same way as they were in a regular AND/OR latch. But now the inputs, instead of being on and off, are AND gates, which take in on and off, but also take in a clock. And as you can tell, the clock, when it's on, lets the signals from these two switches flow through the AND gate, and when it's off, it does not let them flow through the AND gate. So the point is that when this clock is off, I'm not allowed to change the state of this latch. But when the clock is on, then it behaves like a normal latch, because you can think of this as just the same thing as a regular AND/OR latch if the clock stays on. So rather than try to explain this, let's look in logically to see this in action. Okay, here's the exact same circuit that I was just talking about in logically. So I'm in my browser, I have my circuit set up, and logically has a nice tool where I can pause the simulation and go through it step by step. So let's do that. So I'll pause the circuit while the clock is off. This AND/OR latch is in a 0 state, or an off state. So let's say I want to turn it on. Well, first I press the on switch. Now since the simulation is paused, nothing happened. So let's step through it. First, this wire turns on. But then nothing else happens, because the rest of the circuit is still stable. The output of this AND gate has not changed, because there's still a 0 coming from the clock. But since I pressed this button, the clock is now turned on, because the rest of the system is stable. And that's how logically works. Advancing the simulation once more gives a 1 clock signal into this AND gate. So now things should change, because there's 2 1s in this AND gate. So then you output a 1, and there's a 1 going into an OR gate, so you output a 1, and now there's 2 1s here. So you output a 1 goes into this light bulb, and a 1 feeds back into the OR gate, and the system is stable. At this point, the system is stable, so the clock turns off again, after some pause, which logically is ignoring. And if we resume the simulation, you can see that the clock turning off leaves this system in a stable state. Okay, so now you can see how this clock only lets something activate when it's turned on. Nothing happens when the clock is off. So let's see the system turning off. In other words, turning this light bulb off. First, I flick the on switch off and the off switch on, and I step through it. First thing that happens is this wire turns on and this one goes off, but nothing else changes and the system is still stable because these AND gates still output zeros. Clock turns on. 2 1s make a 0. A 1 becomes a 0. And 1 0 becomes a 0. 2 zeros become a 0. And now the system is stable again. So if I resume, the clock will turn on again, but the system is now stable in a 0 state. And if I turn this off switch off, nothing happens. Okay. So you can see how this behaves similarly to an AND/OR latch, except that there's this strange clock thing going on. But it's kind of a nice thing because I can ensure that the only time data is ever changed is when the clock is on. So while the clock is off, I can change my switches. And then as soon as you turn it on again, you start actually manipulating the data in the system. So we have a better sense of organization. Let me give you another example of how this works. This is called a clocked AND/OR latch with 1 input. Here I've taken away the 2 inputs I had before, and I looked now at 1 input called data. And just to motivate this, let me go back to this clocked AND/OR latch and explain one thing that I didn't maybe mention. Right now, both switches are off. That means that nothing should happen. There are 4 states. I can either turn both of these off, both of these on, one of them off, or one of them on. As we've discussed before, turning both of these on is not allowed. but we need some way of ensuring that never happens. This data switch precisely gives us a way to do this. This is exactly the same circuit as before, except the on switch is now the same as this data switch, and the off switch is just whatever the opposite of this data switch is. So whereas in this example, I can turn both of these off, or both of them on, in this example, even if I turn the data switch on, this one's always the opposite of this one. So either you have off, on into these two AND gates, or on, off. So one advantage is you never have to worry about this disallowed 1-1 state. But also you're never in a 0-0 state. So the caveat is that you're always writing data when the clock turns on, because one of these switches is always on. So you have to be careful with this if you want to use a clocked Andor latch with this one single data input. But again, let's look in logically to see how this works. So here I have the same exact thing that I showed you in the slide, implemented in logically. And let's pause and step through just as we did before. So I'll pause while the clock is down. The system is in an off state, so I'll turn it on and step through. First, these wires turn on, and now the system is stable again. So the clock turns on, a 1 passes through the AND gate, passes through the OR gate, passes through the AND gate, and the system is stable again. Now the clock turns off. Clock turns on again, clock turns off again. While the clock is off, I'll turn the data switch off and see whether it turns the light bulb off, as it should. So now this is off. The system is stable again. So the clock turns on. Now there's two 1s going into the bottom AND. So a 1 comes out, which turns into a 0, and then the AND gate at the end outputs a 0, and the OR gate in the middle outputs a 0. And now the system is stable again. So the clock turns off, and the clock turns on. And I can resume, and the system is stable. So let me do this a bit more quickly. So when the circuit is off, I turn the switch on, and it turns the thing on as soon as this clock turns on. I turn it off again, now wait, and it's off. This is kind of the kind of thing that I definitely encourage you to play around with yourself in logically. So after this video, or now if you want to pause it, go into your browser, go to logically, and try to build this yourself and try to exhibit the kind of behavior that I'm exhibiting in this demonstration. Okay, so now it's your turn. There are a few more exercises having to do with these clock circuits. So take a stab at them, and then we'll come back in the third video and finish off the lecture series.